250 tokens per second. Hold on to that number, because it is the one that quietly rewrote a story we thought was settled. The setup: AMD's own published guide for running a giant model across 4 desktop machines contains a table showing 239.1 seconds before the first character appears on a 16,000 token prompt. Nearly 4 minutes of silence. The obvious assumption was that desktop silicon is simply too weak, and you wait for better chips. That assumption is now wrong. The fix arrived on July 31st. It is MIT licensed, it weighs nothing extra, and it is a model, not a machine. This is the deep dive on why the weight existed, what actually killed it, and the arithmetic that still does not work. Start with the 8 days that changed the picture. On July 15th, AMD shipped ROCm 7.14 as a production release, and buried in it was a graduation. The integrated graphics inside the upcoming Ryzen AI Max Pro 400 series, identified in the toolchain as GFX 1151, moved out of the tech preview branch that had run from version 7.9 through 7.13 and into fully supported status. In the same release, VLLM, Llama.cpp, and Allama all became available on the Ryzen Linux path, with Llama.cpp and Allama extended to Windows. That is the boring plumbing news. It matters because it set the table for everything that followed. Then, on July 23rd, AMD held its Advancing AI keynote and put a name on the next box: Gorgon Halo, sold as the Ryzen AI Max Pro 400 series. Free parts: the Ryzen AI Max Plus Pro 495 with 16 Zen 5 cores and 40 RDNA 3.5 compute units. The Max Pro 490 with 12 cores and 32 compute units. The Max Pro 485 with 8 cores and the same 32. The headline spec is 192 GB of unified memory with as much as 160 GB assignable as video memory, and AMD's claim is models up to 300 billion parameters on a single chip. Systems from HP, Lenovo, and Asus are scheduled for the third quarter. And then July 31st, and this is the day that actually mattered. DeepSeek published v4-0731 on Hugging Face under an MIT license, ungated, and moved its official API into public beta. On the same day, the ARC Prize Foundation published independent scores for it. Within a week, the community had done the rest. An August 4th configuration running the full checkpoint on a single AMD data center card drew 382 points on Hacker News. An independent write-up ran the electricity math against the API, and the ARC results thread pulled another 97. Nobody planned this as a hardware story. It became one anyway. To see why a model can fix a hardware problem, you have to separate the two halves of inference. Decode is the part you watch, one token at a time, and its speed is set by memory bandwidth, because every token drags the active weights across the bus. Prefill is the part you do not watch. Before a single character appears, the machine has to read your entire prompt and build the attention state for it. Prefill is not bandwidth bound. It is compute bound. It is dense matrix math, and the amount of it does not grow in a straight line with prompt length. AMD's own table proves the curve. 4,096 tokens takes 39.7 seconds. Double it to 8,192 and it takes 90.5 seconds, which is not double, it is 2.28 times. Double it again to 16,384 and it takes 239.1 seconds, which is 2.64 times. Each doubling costs more than the last. That superlinear shape is classical attention. Every token attends to every token before it, so the work scales roughly with the square of the length. On a machine with a lot of memory and not much compute, that curve is the whole problem. Now the model. V4 Flash is a mixture of experts' design with 284 billion total parameters and only 13 billion activated per token across one shared expert and 256 routed ones, of which 6 fire on any given token. Note that the checkpoint DeepSeek actually ships lists 304 billion, because it comes with a speculative decoding module attached. Residual connections are replaced by something called manifold-constrained hyperconnections. But the piece that matters here is the attention path, and it is genuinely different. The attention is hybrid, combining what DeepSeek calls compressed sparse attention with heavily compressed attention, and it is steered by a lightweight component named the lightning indexer. The indexer does not do attention. It scores relevance, using low-dimensional projections of the latent key-value vectors and the queries, and then the expensive full-precision attention only runs on the tokens it selected. That is the trick. You are no longer paying the square of the prompt length. You are paying for a cheap scan plus exact work on a small subset. Bend the curve, and the weight stops being a hardware verdict. Here is the measurement that makes it concrete. An independent test ran V4 Flash on a single Ryzen AI Max Plus 395, the Radeon 8060S, GFX 1151, with 128 GB of LPDDR5X. Custom quantization at roughly 2.88 bits per parameter. The target model occupies 102.3 GB. A draft model takes another 11.3, leaving 14.4 free. Decode reached 32.0 tokens per second with speculative decoding enabled, against 25.31 for plain autoregressive generation. In prefill, roughly 250 tokens per second on the index sparse path, measured between 246.8 and 255.9 across the 8,000 token validation cases. Now put the two datasets side by side, because that comparison is the whole story. AMD's cluster table implies an effective prefill rate, 16,384 tokens divided by 239.1 seconds is about 68.5 tokens per second across 4 network machines. The sparse path on one machine measures around 250. That is roughly 3.5 times the throughput on a quarter of the hardware. Same silicon generation, same memory, same vendor. The variable that changed was the attention algorithm. And in the same test, exact prefill on short prompts came in at 22.5 to 23 tokens per second, so the sparse path is running about 10 times its own exact baseline. One warning before anyone quotes those figures at a store. Other tests on the same class of box report 6 to 9 tokens per second of decode, and a hardware guide published July 31st puts a 128 GB unified machine at the 3-bit tier around 6, and a 192 GB machine at 4-bit around 25. Those numbers are not contradictions, they are configurations. The spread between 6 and 32 on nominally identical hardware comes almost entirely from quantization depth and whether speculative decoding is switched on. When someone shows you a tokens per second figure for a local model, the number describes a software stack, not a computer. There is a quality axis to that too, and the same guide quantifies it. The 2-bit build weighs 87 GB and holds about 78% top token agreement with the original. The 4-bit build weighs 155 GB and reaches about 96%. The 8-bit build weighs 162 and is bit identical to the release. So the machine that fits in 128 GB is not running the model DeepSeek published. It is running a lossy approximation of it, and the loss is measurable. That is the honest footnote under every desktop benchmark you will see this month. For scale, look at what the same model does when compute stops being scarce. That August 4th configuration runs the checkpoint on one AMD MI300X, 192 GB of high bandwidth memory, 5.3 TB per second, 304 compute units. No weight quantization at all. The checkpoint is shipped, 156.67 GB of weights resident. Prefill lands between roughly 7,900 and 8,500 tokens per second. Decode reads 168.6 tokens per second on a single stream, and a 64-stream burst aggregates to 830.2. Context validated to 256K. That is the same model, roughly 30 times the prefill, on a card that costs more than a car. Now the desktop field, at August street prices. A 128 gigabyte Ryzen AI Max Plus 395 machine runs about $2,900. NVIDIA's DGX Spark, also 128 gigabytes, sits at $4,699 after a $700 increase NVIDIA attributed to memory supply. A used Mac Studio with an M2 Ultra and 192 gigabytes runs about $4,000, and the M3 Ultra version about $6,000. In one comparison at a common quantization, those four delivered 8 to 9, 7 to 8, about 18, and about 22 tokens per second respectively. The Apple machines win that particular race, and they are the most expensive entries. But the rival that actually wins is not on that list. It is the model's own API. DeepSeek prices V4 Flash at 14 cents per million input tokens on a cache miss, 28 cents per million output, and this is the number to stare at, 0.28 cents per million input tokens on a cache hit. 50 times cheaper when the prompt prefix is already in cache. That is the same insight as sparse prefill, expressed as a price. The cheapest way to process a prompt is to not process it twice. In the cloud, that optimization is already shipped, already free, and already the default. On your desk, you have to build it yourself. And on capability, this is not a compromise model. ARC published semi-private results on July 31st. 89% on ARC-AGI, 1 at 2 cents per task, and 61.4% on ARC-AGI, 2 at 4 cents per task, at maximum reasoning effort. Dial effort down, and it reads 87.0 and 56.0 at high, 84.0 and 46.0 at low. DeepSeek's own model card adds 82.7 on Terminal Bench 2.1, 54.4 on DeepSWE, and 54.2 on NL2 repo. Vendor-reported numbers on a harness that has not been released, so treat those three as claims rather than findings. The ARC figures are the independent ones. So run the money, because this is where the romance ends. An analysis published August 4th assumed 20 cents a kilowatt-hour and continuous operation. The Ryzen box draws about 100 watts, 48 cents a day. The DGX Spark about 200 watts, 96 cents. The Max about 121 watts, 58 cents. Against a blended API rate near 13 cents per million tokens, the conclusion was blunt. The best local setup in that comparison costs about 2.4 times what the API costs on electricity alone before you have bought the machine. At 1 to 20 million tokens a day, the payback period is not long. It is never. And the hardware side of that equation is moving the wrong way. Mobile DRAM prices climbed roughly 78 to 83% quarter-on-quarter in the second quarter of 2026. A Bloomberg report in July put DRAM spot prices up nearly 700% over the year, and forecasts have AI data centers absorbing about 70% of high-end DRAM output this year. A 128 gigabyte DDR5 kit was quoted near $1,834 in July. The machine that makes local inference possible is built almost entirely out of the one component the data center build-out is bidding away from you. You can see the same pressure in the tape. As of Friday's close on August 7th, Micron sat around $878, up roughly 7% since our last look on July 31st. NVIDIA was near $223, up about 11% over the same stretch. AMD was around $482, up about 1%, having swung from $429 to $519 inside 2 weeks. Those are observations, not advice, and nothing in this program is investment advice. The point is only that the memory maker is being repriced alongside the chip designers, which is what a supply squeeze looks like from the outside. Three things to watch. First, whether sparse attention becomes the default rather than a flagship feature. If the weight on desktop hardware is an algorithm problem and not a silicon problem, then every model that ships without an indexed path is leaving the local market to the ones that have one. Second, whether anybody publishes a proper time-to-first token table for a sparse attention model on a 2-node cluster. Right now, the vendor pages give you the recipe, and the community supplies the stopwatch, and those two groups are measuring different things with different tools. Third, the machines themselves. Gorgon Halo systems are scheduled for the third quarter, which is now, and the question is not whether 192 gigabytes holds a 300 billion parameter model, because it does. The question is what it costs to fill those 192 gigabytes in a year when a 128 gigabyte kit is quoted near $1,800. Watch whether AMD's partners publish prices at all, and watch whether the quality tiers get standardized, because until buyers can compare a 2-bit build against a 4-bit build on the same page, every benchmark in this category is comparing different models wearing the same name. So here is the one-line version. The 4-minute wait was never a verdict on desktop silicon. It was a verdict on classical attention, and a model released on July 31st under an MIT license bent that curved by roughly a factor of 3.5 on a quarter of the hardware. That is a real engineering win, and it deserves the attention it got. What it does not do is change the arithmetic. At August prices and August electricity rates, running this model at home costs more than renting it, and the memory market is pushing that gap wider, not narrower. Which means the case for local inference in 2026 was never speed and was never savings. It is that the weights are MIT licensed, the context is a million tokens, and nothing you type leaves the room. That is a good reason. It is just a different reason than the one on the box. Sources are listed in the description in order of appearance. Market data comes from a finance, and nothing here is investment advice. If you want the industry read rather than the press release, subscribe. We do this every day.